A beam of mass m equals 24 kilograms and a length L is hinged and extends outward perpendicular to a wall as shown. A string is attached to the end of the beam. Okay, string right there. With the other end attached to the wall, distance L over 4 above the hinge. Okay, the tension in that string is 710 newtons. Okay, so I'm going to write this up real quick. So we have a click, blue, that direction, tension, which equals 710 newtons. And I might call that force tension. Nah, I'll just go to tension. Tension's fine. A mass M hangs a distance L over 3, check, from the hinged end of the beam. Okay, so to conceptually understand what's going on here, first we should look at this hinge right here. So it looks like the hinge is kind of like one of those, So the hinge, it looks like it allows movement to rotate like this, but it doesn't allow motion like this. And it doesn't allow vertical motion like this. By not allowing the vertical or horizontal linear motion, what that means is it allows there to be a normal force vertically or horizontally. And that's important because we don't really know what that is and we can't really calculate it, which is going to force us to calculate things through torques, but not force. On our previous example, we had a ladder that was able to slide either vertically or horizontally. And that ability to slide meant that we knew what the linear forces could be, and we could basically balance them out. But this one, since we have basically mystery normal forces here, and the normal force is just a reactionary force, like I push against the wall pushes against me, and by the wall pushing back against me, there's no motion. The total net force is 0. So that is what's meant by a normal force. So this hinge can exert normal forces, x or y, but it allows angular motion. Okay, what is the x component of the force exerted by the hinge on the beam? So this is asking us for the normal force. X component is a force exerted by the hinge on the beam. Okay, so I'm going to say this is the normal force. So basically what it's saying is the x component of the force here. So we have this tension pulling this direction, which is going to have an x and a y component. So something kind of like this, tx and some sort of ty as a decomposition of that force due to tension. Well, the hinge is going to have to exert a force in the opposite direction, a normal force if you will, to prevent relative motion. So that the sum of all forces in the x direction will equal 0. Because this whole thing is stationary, it's static. Okay. So what we have here is we have a triangle. And so we have tension equals 710. We have a distance equals L over 4. We have a distance equals L, because 2/3 L plus 1/3 L equals 1 full L. And so we look at our SOHCAHTOA, good old SOHCAHTOA. There are a few things in life more useful than that mnemonic. So we have an opposite, we have an adjacent, opposite and adjacent. Tangent of theta equals opposite over adjacent. Therefore theta, which is what we want here, equals arctangent of opposite L over 4 over L, which equals arctangent of 1/4. Now, a more correct way to do this would be we could solve for the hypotenuse here, which would be L squared plus L squared over 16. 16 is 1/4 squared, square rooted, and then we could use that with the SOHCAHTOA to find the angles. I'm just going to find the angle in terms of degrees because it's easier, and we're not going to be that accurate here. We don't need to be perfect. So we'll go mode make sure we're in degrees. Make sure we're in degrees. Quit, we'll do second arctangent of 0.25, which is 1/4. And we get 14.037. 14.03. Is it 7? Doesn't matter. It doesn't. 0.036 degrees. And that's what theta is. Okay. So from here then, we can then decompose our tension vector into our components. Because this tension is going to follow the same components as the angle. So nope, that's not Tx, that's just T. This will be Tx, this will be Ty, and Tx will equal, come back to here, we'll do cosine this time, cosine, second answer, times 710. And that gives us a relatively big number, which makes sense, because it's a small angle. So we have 688, 688. I think that's a submarine number. 688.8. Okay. 0.8. And that'll be newtons. Okay? So what is the x component of the force exerted by the hinge on the beam? Right here. 689. 688.8, rounded up slightly. 689. I'm going to call that a win. Determine the mass m hanging from the beam. Okay. So this is static, stationary, not moving. Therefore, the acceleration in both the x and y direction, linear, but also the angular, clockwise and counterclockwise. I guess technically the torques would be plus and minus z. Not important. The torques are also equal 0. So this would be sum of torques equals 0. So you can also think of this torque as IA, where I is the moment of inertia and A is the angular acceleration. This is basically the angular equivalent of mass, a weighted mass distribution number. And then alpha is, so alpha R equals A, acceleration. So long story short, alpha is basically angular acceleration. So what we're going to say is, go back to purple here, the clockwise and counterclockwise will equal each other. So we'll start by finding the Ty, this number right here, which is, let's see here. Can I go back up? Is there a way to do that? I should be able to, I'm not going to. Okay, so we'll do 710 times sine of 14.036. That gives us a small number, 172.2. 172.2 newtons. So we'll look at torque in the, I'm going to start with the clockwise direction. Not for any real reason, other than I just kind of what I want to do. So we look at the definition of torque. Torque will be R cross F. And another way to think of this cross product is it's the R that's going to be perpendicular to the force. So we have the force coming up. So this will be the Y component of the tension. So I'm going to call this tension Y. This will be R, the perpendicular R. And that length here is going to be 2/3 L plus 1/3 L, which will be 1 full L. So we have L times 172.2 newtons. And I'll say 172.2. I'll say 172.2 L. So you might think cross product sine of theta. Well, that theta is right here. And what we did then is there is sine of theta involved. That's how we converted the 710 into 172. So you can take the sine, you can think of it as sine of theta times either the radius or the force. Either one works. Okay, so that's the torque in the clockwise direction. Now we want to find the torque in the counterclockwise direction. So there's going to be two components to this torque. We're going to have R, I'm going to call this beam, times force cross beam, plus R ball cross force ball. I know they're both start with B, which makes it difficult, but maybe instead of beam I could have used bar. No, that's just as bad. Okay, so we'll look at these. The R in this case will be the distance from the hinge. So for the beam, we're going to say that the beam can be modeled as all the mass at the center of mass. So 24 kilograms, 24. So this will be, and this will be due to gravity. So we have L over 2 times 24 kilograms times 9.8. Mass times gravity. That's the force. Plus R of the ball. I think that's L over 3. Check real quick. Yep, L over 3. Times, wait a sec, force the ball. Do we know the mass ball? No, we know mass ball. That's what we're trying to find. And that will equal up times gravity, which will also be 9.8. So, hindsight, I probably should have just left gravity as a constant. Live and learn. So we know that the magnitudes of these will be equal to each other. In reality, you could think of it as torque clockwise plus torque counterclockwise equals 0, but then you move one to the other side and you can say that they're equal. So we have, can I just copy paste here? I'm going to try and copy paste. That would be convenient. Nope. Copy paste. Nope. There we go. Copy paste. Excellent. That's working more efficiently. Though I probably should use a color other than purple. So now we can cancel the L's. We can move this over to the other side. So solving for mass of the ball, we'd have 172.2 minus, I'm going to call this 12, minus 12 times 9.8 all over 9.8 times 3. Does that seem reasonable? Sorry, so this moved over there. That multiplied by 3. Yeah, maybe. I'll make this bigger and more obvious. There we go. We're going to go to the calculator. To the calculator. On. Clear. 172.2 minus 12 times 9.8. Pretty sure that gives us a positive number. Excellent. Times 3 divided by 9.8. 9.8 equals 16.71. 16.71 now we measured in kilograms. So 16.71 gives us, that is, I like to round, I don't like to round that much, but 16.7 does round up to 17. And these are just going to, is that two significant figures? Maybe. No decimal point, to the largest whole number, or the closest whole number. So I'm going to call that good. So I'm going to take this. I should probably leave that bottom part just in case. Maybe I should leave it all just in case. Okay. So if the mass, M, is moved to the left so that it hangs from the beam at a distance of L over 2 from the hinge, so it's moved to the left, okay. Whoop. The horizontal component of the force exerted by the hinge on the beam will be... Okay. So what this is saying here is we move the ball out. So when we move the ball out, this number right there will get larger. Because we'll go, that number, the 3, will get smaller, but it's divided by, long story short, more torque. So we're going to, when we move this ball out, we're going to get more torque this direction. Which means that to compensate, to keep everything steady, we have to have more torque in the opposite direction to keep it from moving. Now that torque is going to come from two things. One from the radial arm, this, I'm going to call it R perpendicular, but that's going to be constant because that beam is going to stay the same size. So the one thing that we can change though is tension. So we'll need tension in the Y direction. Well, tension in the Y direction is simply related to the tension total. It's specifically the sine of I don't know what, 14 degrees times the total tension. So the total tension has to get bigger. So if this total tension gets bigger, but we still maintain the same angle here, that's how we get a bigger Ty. But that's also going to imply a bigger tension in the x direction. So by moving the ball M further out, more to the left, then what we're going to have is we're going to have a more tension in the x direction as well. So if the mass M is moved to the left, check, so that it hangs the beam, okay, from the hinge, the horizontal component of the force exerted by the hinge on the beam will be greater, larger than when the mass was at L, was larger than when mass was at L over 3. So to recap real quick what I said with that, because it was a long train of thought. So we move the mass out. That means that it's going to provide more torque in the counterclockwise direction. So for it to stay stationary, we're going to need to compensate for that by having more torque in the clockwise direction. Well, that torque comes from both the tension Y, the perpendicular tension upwards, and the radial arm. The radial arm, the beam, stays the same size. So the tension in the string, rope, has to go up. Well, if you have this triangle and your Y component goes up, well, your hypotenuse is also going to have to go up, which means then also that the tension in the x direction is also going to have to go up. And that's the kind of sequence that it's going to follow. And that's why we're going to have a larger x component than tension pulling it this way, which means that the reactionary force, the normal force from the hinge going to the left, will also have to get bigger. Whew, that's a long, convoluted train of thought. So that's how this problem is approached. Hope it helped. I will see you next time.